Hi, welcome to another repair video tutorial. This is a Hisense LCD32W57, and the problem with it is it's dead, according to the customer. There's something rattling inside the unit, so what I'm going to do, rather than plug it in like I would normally do to see what's wrong with it, I am going to take the back off first to see what is rattling around. So I'm going to pause the camera now and reposition the unit with the back off. I have the back off, and what I can see here is down, just how the camera shot down here, there is a fuse just sitting there. The fuse in itself doesn't look like it's blown, but certainly the fuse in here looks blown. So I'm just going to check and see, are the fuses, someone replaced the fuse with an underrated fuse first. As you can see, that there is pretty black. Can't see any markings on the replacement fuse, so it's hard to tell what it is. I'm just going to check this original fuse to come out of it and see, is it okay. The original fuse is okay. And rather than just put in a fuse and blow it again, what I'm going to do is I'm going to check for shorts on the power supply. To do that, I'm going to have to remove the power supply. Take all these cables off. They just clip out. And then we have 6 screws. A closer shot there for you. That's the power supply out. So what I'm going to do is now I'm going to start repositioning these this TV and the camera and start doing a bit of fault finding on this board. I'll pause the camera. I have a little circuit diagram drawn of the input of this power supply. What we have here is the mains coming in live and neutral, which is at around 240 volts AC coming in here. And it goes through a fuse, F801. This is the fuse that I've seen burnt out. Then it goes through this filter network that you would see on all power supplies to prevent noise from the power supply getting back into the mains, or noise coming from the mains into the power supply. And then you got this AC to DC converter, bridge rectifier block, where the AC comes in and it comes out here at DC. So you'll see here about 385 volts DC at this particular point here. The first thing I am going to do on this power supply is put an ohm meter between here and here to see, have I got a short. And then what I'll do is from here to here. I could just plug it in with a new fuse in it, but it will go bang if there's a short. So and it'll do more damage. So first of all, I'm going to check for shorts, and if I don't find the short, then I will put a fuse in. This here is where the live and neutral come in. This pin here is live, goes through the fuse, F801, and then it goes into this filter block here. From here to here is the filter block. You see these little symbols for coils. Okay, what we'll do first is we'll check between the live and neutral pin. If it's faulty, you'll hear that. Okay, but I always reverse the polarity as well because of that diode pack in the bridge rectifier. Okay, so we're all right there. And then what I do is I come along and check for continuity all the way back here to my fuse. Okay, because it's both in there, we have continuity. And likewise, here's our neutral. You have this little thermistor here as well. That's okay, it's not open circuit. And it goes all the way back there to neutral. So what have we done there is just checked from between these two pins here and then reverse the polarity of the meter, and there is not a short here between here and there using your meter. Now however, I did find if you put high voltage across something, if something breaks down under high voltage, you will not see it with a meter. At least this gets any obvious shorts out of the way and stops it putting a strain on the print and the other components on the board. Then what I did was I checked for continuity between here, this is the AC into the bridge rectifier pack all the way back down here to neutral, and on the live side all the way back here to the input at this side of the fuse, because that fuse is not in the circuit. Now what I'm going to do is I'm going to check for a short between here and here on this capacitor. You'll see that C810, and here it is. This is the positive side, this is the negative side. So if I put this between here and here, and we're getting you get a buzz for a minute until the capacitor charges up. That's the positive, and it goes all the way back down here. That's the switch mode power supply transformer, and then it comes all the way back over here to the positive side of the bridge rectifier pack. Okay, we checked between here and here on the bridge rectifier pack, circuit reference number M13, and I put the meter between these 2 points here, and we had no short with the meter. That doesn't mean when I plug it in that when 385 volts is going across these 2 lines, something is not going to break down. Its insulation is not going to break down under high voltage. But like again, it gets rid of any obvious short circuits. I'm going to check this bridge rectifier pack, and the way you do that normally is you just put your meter across the pins, and you shouldn't have a short between any of them. So here's our bridge rectifier pack down here. Here, a little bit of a beep when the capacitor is charged in circuit. Turn around, a little bit of a beep between these pins. Nothing, nothing. Now we do between here and here. There's no obvious short on the bridge rectifier pack either. What I'm going to do now is put that fuse back into the power supply and put mains to it and see does the fuse blow. Okay, I have the power supply back in the unit. I've replaced that 4 amp fuse, and I have the mains cable connected into the mains socket. What I'm going to do now is just switch it on and cross my fingers that that fuse does not blow. It'll either go bang, or you might see a flash now on the camera. So I'm going to reach over now and press the on off button, and as you can see, it's blown straight away. What I have to do now is take this power supply out and try to isolate where that fault is. There's some insulation breaking down in this power supply. That's not an obvious short. The next step I have taken is remove this transformer. It's a little power factor correction transformer, and it goes between this. I'm not showing it on this little circuit diagram. It actually goes between the bridge rectifier and this filter network. I have removed this out of circuit, and what I'm going to do then next is I'm going to plug back in the unit. Here's the power supply. I have soldered 2 wires onto the PCB. Live goes to the fuse, neutral goes to this end. I am using a isolation transformer for this, and this next test I will be doing will be with a live power supply. So if you don't know about know how to work on live mains safely, don't continue any further with this. What I'm doing. Right, let's just turn over the board. And our fuse is down here. See, can we get a close up of it? Right there. Okay. What I'm going to do is I'm going to plug it in, and then you can see, does it blow? Okay, it's plugged in to the isolation transformer, and it didn't blow. I'll plug it back out. Turn over the board. This is the area I removed this transformer out here, and this is where your live and neutral. Here's your live, and this is your neutral, where it goes into that power factor correction and then back out. Okay, I'm ready to plug in the unit now. I'll do a few live checks. Plugged in. Turn my meter to AC. And what I'm going to do is I'm going to check between here and here. I should have around 240 volts. Okay, as you can see, there's 241. So we don't have any problem. Just plug this out first. So we don't have any problem in the circuit from the live to this filter pack here. The next thing we're going to have to do is check this power factor correction transformer, and I'll solder this back into the board. I will leave the two leads that come into the power factor correction soldered into the board, but the two that go to the bridge rectifier out of circuit, you can see them here. Here's the filter network. We would have the power factor correction in here, and two of the prints go to the input of the transformer, and then two go out to the bridge rectifier. Okay, what I've done now is I've resoldered this transformer back into the circuit. I've soldered this end of the transformer, power factor correction transformer. These have not been soldered in, so they're left without any solder on the legs. Let's see, can we show you that on the board? Yeah, that looks like a clear shot. Here's the AC coming in, and here's the AC coming out on these two pins here. Okay, what I'm going to do now is plug it in to my isolation transformer and measure the input of that power factor correction circuit. So we have 250 volts there. That does change with the demand that's on the mains of the area I am working from. Okay, we have 250 volts. I'll just unplug the power supply. Let's see, can we have a look? So we can safely say then most of this circuitry from here to here is okay. What I'm going to have to do now is start checking this secondary, the output of the DC converter, this bridge rectifier M13. And how I'll do that is I will start removing components out of circuit. I'll have to draw another diagram for that. Our circuit this side of the bridge rectifier here is all okay. What I'm going to do now is check some of this circuitry here on the output of the bridge rectifier and the bridge rectifier. There is some components that are not shown on this diagram. I'm only showing major components. I'm not showing little capacitors that would be associated with this bridge rectifier. I'll get down to that if I find that it is around the bridge rectifier. We have our output transformers here, our smoothing capacitor here. These are all components that could be given breakdown of insulation. I'm not saying it is breakdown of insulation, because I've also seen a short on the secondary side do this as well, where you got a fuse rated at 4 amps and the current is more than 4 amps, but not enough to trip the overcurrent protection in some poorly designed power supplies. But that would be rare. I have to check this insulation first. For me to do this, the next thing I'm going to do is I'm going to disconnect here a T801 and T802. That takes the transformers out of circuitry and the drive transistors, FETs. For our purposes at the moment, we don't need to know if it's an FET or a transistor. And let me see, can I get this in shot? This here is T802, which is the standby transformer, and you know by the size of it, it's a smaller transformer. And here's your main transformer here that gives out the higher voltages and drive the screen, the lamps for the screen, etc. I have unsoldered the pin here, and I've unsoldered 2 of the pins on this. And what I'm going to do now next is plug it in and select my DC voltage on my meter and plug it in and see, does that fuse blow. Okay, I'm going to plug it in now and cross my fingers, and the fuse blew straight away. I could see the flash. I don't know if the camera picked it up. The fuse blew, but what I'm going to do now is check the voltage across that smoothing capacitor. And as you can see, we have 233 volts across that capacitor, even though it blew the fuse. I am going to now have to go back to that bridge rectifier circuit and check it out. I removed this bridge rectifier from the circuit, and I'm going to do a few cold checks on it, because something shows up now that was not in my initial checks on this when I've done cold checks on it. Maybe it's all the repeated blown of the fuse has stressed the component, because I said initially there was no shorts on that bridge rectifier. But let's see, can we rig up a meter, put on the diode check. And what I'm going to do now is, here's our bridge rectifier pack that's come out of the unit, and how you do that is by just doing your diode check across this, and just keep an eye on the meter. And as you can see there, we have a dead short between them 2 pins. See, it's showing up to 0. We should be getting around the 0.5, 0.6 of a volt drop across a diode. They are correct, the rest of them. So we have one shorted diode in that diode pack. I'm going to see, can I get one of those and put it in. Okay, I found a replacement bridge rectifier pack for the faulty one. The faulty one was type D5SB60. It's rated at 600 volts 6 amp according to the data sheet I have here, and the one I am going to put into it is a GS IB660, which is always also rated at 600 volt at 6 amp. And what you also got to make sure is that let me see, am I getting that in the screen, that the pinouts are the same. Here's my minus, which is the same as this. Here's our live and neutral. The AC comes in here, AC comes in here, AC comes in here, and here's positive. So the pinouts are the exact same. You don't want ones that are different, like you have your AC on the outside pins. You'd have to do a bit of rewiring if you wanted to do that. It's not impossible, but it's just messy. This here is our positive pin here. There's 4 holes for this bridge rectifier pack to go in. So I'll line my positive pin, which is this, up with the positive pin on the board. And now I'm just going to solder it in place. The clue to the bridge rectifier being gone was more than likely that we had some kind of voltage on the reservoir smoothing capacitor. That meant half the bridge rectifier was working. Now I'm just going to resolder back in those transformers. There's one back in. And I'll have to replace that fuse. What I did there was I was running short of 4 amp fuses, and I had lots of 3.15 amp fuses, and this board was being tested out of circuit, so it wasn't going to draw the full amperage. You might get an initial surge at switch on, but the 3.15 should have done it, and that would be normal if you were running that short of a higher value fuse. If you had a load of lower values, you could use them just when it's out of circuit. It wouldn't work if it was in circuit, because the total draw when the TV is up working might be more than the 3.15 amps that I would be putting in it. Now what I'm going to do is I'm going to clean up that PCB, and quart of alcohol. Just get rid of all that flux. Dry it off a bit. And I'm going to put a 4 amp fuse in it now. All going well now. This should not blow. Just going to line this up so we can check it out. Our fuse is down here, and it blew at plug-in. So right, I'm just going to plug it in now and see what happens. Okay, fuse is intact, didn't blow. So what I'm going to do now is, now remember, this big boy here, this smoothing capacitor, stores a charge. So don't be careful of the board. You might get a few belts off it if you touch any of the print, even with it plugged out. As I can demonstrate to you now, we'll have a charge stored on that. I'm just going to go up here to 600 volts on my meter. Okay, I'm going to put my meter across this smoothing capacitor, and it's plugged out, and we have a charge at 240 and decrease them slowly. If you put your hand across that capacitor, you will get a nasty burn off it. So always remember to discharge these smoothing capacitors. You can use a normal bulb, mains powered bulb, like you see in your overhead light. You could wire up a connector on one of those, or 2 leads, and just put across that capacitor. Some people just use a resistor, high value resistor, to discharge it. What I don't advise people to do is put a conductor across it, or a screwdriver across it, or pliers to discharge it, because it'll make a big bang and it arcs. It can cause damage, so don't do it. Discharge it correctly, or wait for it to discharge. It will discharge slowly over time. As you can see now, it's down. I'll put the leads on the right terminals, so we're down to 211 volts now. What I'm going to do next is I'm going to put this PCB back into the TV, power it up, and see what we have on the screen. Okay, the power supply is back in the unit, and all the connectors are back on. Screws are in, and what I'm going to do now is plug some mains into it and then switch on, and we'll have to cross our fingers that the fuse doesn't blow again, because you could have a short on the secondary side that's drawn too much current. Let's see what happens. Right, what we'll do now is check some secondary voltages, see if we got any. Now I'm sure we have, because I can see a light, standby light over here, but let's just check and see. I'm going to check this connector over here. Let's get a close up of the connector. Okay, we should have 5 volts. There's 5 volts. And there's 12 volts. And I'm sure we'll have 24 volts then if we take it out of standby. Let's see. Okay. This connector over here should have the 24 volts on it. It looks like it's powered up and it's working. So I'm just going through the voltages here. So we have 23.8 volts going to the inverter PCB, which is about right. And I can see the backlights up working. So I'm just going to reposition the unit and have a look at the picture. Okay, I have the back on the unit, and I'm just now going to plug it in and see what type of picture we have. Blue light is on over here. We've got a start up, and we have our test bars up. I'm just going to check to see if we got sound. Okay, alright. That was a nice bit of fault finding for a change. The procedure for finding shorts on a power supply would be like that. If you can find an obvious short circuit with your own meter, there would be no need to go through all that disconnected. But because that diode was not showing up a short circuit initially, I had to do a few isolation checks, like disconnect part of the circuit. The biggest clue I should have had on it was there was some voltage on the reservoir capacitor, which would have meant that everything on the DC converted side of the bridge rectifier was okay. Otherwise you would have 0 volts there, would have shorted. So what was happening was you were getting half wave rectification. One half of the rectifier was down, and you were just getting half of the wave, so it was charging up that cap. And then when it come to the next cycle, the other wave, of course that diode was short and it just blew the fuse. Of course this happens 50 times a second, so it's so quick. I hope that video is of some use to someone out there. Thanks for watching.